I think that we can get started. Yeah, so it's our pleasure today to have Alex Bienstock. So Alex is a third-year PhD student working with Evgeny Dodis. He works on many things, including understanding the security of secure messaging and Wichicast agreement. And today he's going to tell us a little bit more on how to make encrypted RAM forward secrets. So you can take over, Alex. Thank you again. Yeah.
All right. Yeah. Thanks for the introduction, and yeah, thanks again for having me. So yeah, this is a paper on what we call a forward secret encrypted RAM. And I'll talk about lower bands for this primitive and also some applications of this primitive. And so, yeah, this is joint work with my advisor, Yevgeny, and also Kevin Yo. Okay, so yeah, what is forward secret encrypted RAM? Well, it's been extensively studied under a number of different names for, the past few decades, actually. And in general, its goal is to privately and forward secretly outsource the storage of a large data array using small client storage. Okay, so a little bit more specifically, starting with let's say the security model, basically the adversary always sees the server storage and also, the individual cells that the protocol touches in the server storage as part of the protocol. And we want forward secrecy, meaning that, if the client storage is leaked, of course, everything that is stored in the RAM at that moment is insecure, just by correctness. But we want everything that has, already been deleted or overwritten to be secure. Okay, and yeah, you want the typical, read-write functionality of a standard sort of RAM. And for these read and writes, we of course want them to be efficient. And for this talk, we'll assume that there are a static number of entries, n. Okay, and also in maybe the sort of concrete efficiency realm, we want to use sort of practical, namely symmetric crypto. Okay, so first let me talk about maybe a trivial solution, which is maybe the sort of standard sort of outsourced RAM solution that you would use, okay, if you didn't want forward secrecy. So yeah, what you would do if you have these 8 data elements is you would just encrypt all entries with a single key and store this locally, right? So on the client side, we have this key, and then on the server, we just store the encryptions of all of the data under this key. Okay, but then if we want forward secrecy, if this key K is somehow leaked to an adversary, then we need to refresh this key after each write, right? Because if we want something to be deleted, then we need to, forget about this key K, which means, yeah, we need to resample it and then also re-encrypt everything, which is, rather inefficient, right? That basically you need to, yeah, do a omega n work per operation, which is bad. So the folklore solution is sort of a tree-based solution. So you store the root of this tree in the client side, which is some encryption key. And then you sort of go down this tree where at each node, there is a different key that is encrypted under its parent. So, or the other way around, the key at every node encrypts its 2 children. Okay, I need to admit somebody. Okay, so yeah, if we keep going down like this, then this key K0, the left child of the root, will encrypt its 2 children, K00 and K01. And all the way down at the children, we have the data elements encrypted by its parents. Okay, so how do we read with this solution? Let's say we want to read the 4th data element. then we start by taking this root key, k epsilon, decrypt k0, decrypt k01, and finally decrypt d4. So, pretty simple, and we get logarithmic overhead for reads. And as you might imagine, writes are fairly similar, except in addition to what you call the direct path to the fourth cell, you also need to retrieve what's called the copath to cell 4, which means all of the siblings hanging off of this path. Okay, so again, you take k epsilon, you get this direct path and copath, then you first use k epsilon to decrypt the two children, k0 and k1, then you use k0 to decrypt its two children, and so on, right? And then you forget all of the keys that are on the direct path, and remember everything that's on the copath. And this is what gives you security. I'll touch on it more in a second. And once you've done this, you basically resample all of the keys on the direct path and do all of the encryptions again. Okay, so you resample this k01 prime, encrypt its two children, including the new data element d4 prime, resample k0 prime, encrypt its two children, and then resample k epsilon prime and encrypt its two children. And so we achieve forward secrecy from this because all information about d4 is gone, right? So like before, you had that, there was some encryptions of d4 up the tree, under sort of like, ancestry of keys, let's say. But now all information on these keys is gone. So if this k epsilon prime is corrupted, then the adversary can't find anything out about d4. Okay. And so the efficiency of the solution is, of course, constant client storage. You're just storing a key, and linear server storage, just a tree of encryptions, and log n overhead for both reads and writes. And if we want, we can even say we want to store some S keys on the client side instead of just one, where let's say S is much smaller than N. Then what we can do is we can just split the data amongst S different trees, and we still get big O of N server storage, and then log N over S overhead instead. Okay, and as I said, this primitive has been studied for some 2 or 3 decades, and the main question that we answer in this work is this solution optimal? Because this folklore solution, it's very simple, it's been known for a while, but there hasn't been any improvements since. And our answer, unfortunately, is that yes, this is the optimal solution. Okay, so let me just outline the rest of the talk. First, I'll talk about the intuition of this lower bound, which means first going over this symbolic model in which we prove it, and then the intuition of the proof itself. And then I'll talk about some applications that in some sense circumvent the lower bound. These primitives are called forward secret memory checkers, oblivious forward secret encrypted RAM, and forward secret multicast encryption. Okay, and by the way, if you have any questions during the talk, please, don't hesitate to unmute yourself.
Yeah, I have a question.
Sure.
Could you say a little bit so you mentioned that it's been studied for quite some time, but could you say a little bit about in what context and what the motivation was, or what?
Yeah, I mean, I think like as far as I'm aware, I mean, I don't know about the bigger context, but yeah, I guess people have been studying some form of forward secrecy for a while now, under different names. Yeah, sorry, I can't exactly remember the different applications in which these papers use the primitive. Yeah.
I have a question.
Sure.
So when you say optimal, what sense do you mean optimal in? And also, is the question just, is this the most efficient forward secure ERAM that's possible? Is that the optimal part that you're going
for?
Okay.
So I'll talk about the model a bit in a second. But basically, using, let's say, standard symmetric key primitives, what is the most optimal in an asymptotic sense protocol for forward secret encrypted RAM?
Great, thank you.
Yeah. So yeah, maybe let's dive into the model a bit. So first, I want to provide some intuition on why we chose the model that we use. Okay, so as many of you probably know, the sort of holy grail for data structures lower bounds is called the cell probe model. Okay, but unfortunately for this problem, it seems like it's too powerful. And what I mean is sort of the essential part of the cell probe model is that it only counts cell probes towards the cost of a protocol, and sort of says every other kind of computation is free. Okay, but at the same time, it requires the adversary itself to still be PPT. So in this model, there is a trivial big O of 1 solution. Basically, every time I write something to RAM, I just sample a random AEAD key, encrypt it, and do some sort of authentication as well, send it to the server, and then when I want to read, I just try every key until I get one that succeeds, and decrypt the corresponding cell. Okay, so it seemed like the cell probe model was therefore too strong for us. Another common model that's used is called the balls and bins model, but this model is actually too weak for us. And this is because in the balls and bins model, the server cells can only hold either the data elements in the clear or sort of encrypted data elements and nothing else, which means namely that the folklore construction itself is not captured because on the server we also hold encryptions of keys, right? So this isn't captured by the balls and bins model. Okay, and so in the end we settled on this symbolic model, which originally was introduced at least for lower bounds in 2004 by Michiancio and Penjuani. And recently, many people have started to use it, including us, in the context of secure messaging. But I guess with this paper, maybe we're hoping that people might start to use it for private data structures as well. Okay, and yeah, it's sort of the perfect in between of these two models, at least for this paper. Okay, so yeah, I'll try to.
I have a question, Alex.
Sure. Yeah.
So in the cell probe model, so you said that there is this trivial solution that uses authenticated encryption, but maybe I'm wrong about what I'm going to say, but it doesn't mean that it's not possible to have some lower bounds in the cell probe model. It's just that the solution that you are thinking about, which is O1, that use AEAD or authenticated encryption, doesn't work because it requires something that it doesn't have PPT. But it might be there is a solution that it's okay, maybe that achieves maybe better than logarithmic, or maybe something like that. But is it right to view it as still an open question, or is it like something that we cannot prove it at all in this model?
So yeah, I mean, to be honest, I'm not like an expert on the cell-probe model. I think, Kevin, our co-author, is more of an expert than I am on this. But I got the sense that, because a protocol can use unlimited computation, there's not really much you can do in improving a lower bound because we have this trivial solution. I think at one point Kevin said, there are ways to sort of maybe require the protocol to use bounded computation as well, but then there's like maybe sort of weird tricky things you can do, and like using different security parameters, for example. I think like generally it gets hairy if you try to change the cell probe model away from this.
Okay, I see.
Does
So
that answer
no,
your
I see. I mean, I see. My intuition. It seems like that it's tricky, but I understand that it might be like some other, like other requirements here that maybe I'm dismissing here, like because I'm thinking that maybe since here it's not PPT and you can come up with a solution, then you violate the cell probe model. Then I was just thinking maybe, as you were saying, exactly, like maybe there is a way how to come up with a bounded type of protocol that leverage maybe authenticated encryption, and you can still make it work. But since Kevin thought already about it, and that's
I see. Okay, yeah. I mean, yeah, maybe giving another answer for the question then. Yeah, our symbolic model is definitely not unconditional like a cell probe lower bound would be. So, our model lays out a number of assumptions, sort of like a black box separation, right? Like a black box separation only rules out solutions that use some primitive in a black box way, right? Our model, as you will see, is kind of similar in that it lays out a number of assumptions and says, if the protocol follows these assumptions, then the lower bound holds. But there could be some protocol which, doesn't obey these assumptions, and it could be, it could break our lower bound.
I see.
And in fact, like if you assume something like puncturable encryption, which to my knowledge is like basically only known from stuff like IO or like functional encryption, then you can overcome our lower bound.
Yeah, thank you.
Yeah, but it's a good question. Yeah. So yeah, maybe I'll explain the symbolic model itself. So yeah, basically the idea is that the protocol is allowed to store in server cells some strings that are arbitrarily derived from some structured grammar. Okay, and this grammar is sort of specified by our paper for this specific problem. But yeah, I guess like any paper could define its own grammar. But yeah, let me just talk about what we use. So basically, server cells can hold encryption or PRF keys, even dual PRF keys, which are basically just random coins. They could also hold ciphertexts, also secret shares, and data entries themselves, of course, and then also sort of arbitrarily nested combinations of the above. Okay, so the specific grammar that we use is the following. Okay, so yeah, basically everything that I said above, and then also, sort of allowing for nesting these, you see these big C's, which are the starting point here. So you can sort of nest these arbitrarily as well. So some examples are, maybe some random string R, another random string R prime, some, crazy encryption of a PRF invocation on R, of some secret share, and so on. So I guess the point is like the model allows for quite general use of these certain primitives. So, okay, does that make sense for now? I guess there's no questions, so, okay. So, and then on top of this grammar, there's also sort of these derivation rules, which entail what the protocol and what the adversary can actually do with these symbols, right? Because these symbols that are derived from the grammar have no meaning, right? They're just, so it's also like a sort of an entirely different model of computation in some ways, in that, you know, you're not looking at like any bits or, you know, group elements or anything like this. These are just abstract symbols that on their own have no meaning, but this so-called entailment relation actually captures their meaning. And, you know, it's really just the standard meaning that you would think. So you can only, you can decrypt a ciphertext if and only if you have its corresponding key. Okay, and yeah, basically, you know, maybe if you didn't know its key in the standard model, you could like try to brute force it, whatever. But of course, you know, this would take, you know, a super polynomial time. And so the symbolic model sort of just says, if you don't have the key, you don't have the plain text. You can't get the plain text. That's how it deals with this sort of thing. And so, yeah, similarly with a PRF key, you can compute any output of the PRF. Okay, and so back to our example from the last slide, if we're using 2 out of 2 secret sharing, then yeah, if you have all of these strings, then yeah, so first using R, you can derive this PRF key, which then allows you to decrypt this sharing. And using these 2 shares, S1 and S2 of this of the encryption, you can of course put them together to get the ciphertext itself, and then use this R prime to decrypt D1. Okay, and so this is like the only power that we give the adversary, essentially. Okay, but you know, of course, it does correspond to reality, you know, quite tightly, right? Okay, and so we use what's called a key data graph in our lower bound to somehow abstract the encodings of what's in the client and the server cells, and also the data array itself. Okay, and for simplicity in this talk, I'll only consider you know, PRF and encryption for allowed, you know, the allowed primitives. And so defining it based on this, at each time t, which, you know, basically corresponds to, the steps correspond to the different operations that the protocol takes, okay? We have this graph where the vertices intuitively are the keys that have been sampled and are still accessible by the protocol at time t, and additionally the data entries at time t. Okay, so yeah, basically what I mean by accessible is using this entailment relation that I discussed on the last slide. Okay, and then the edges are, for example, if you have a PRF of U, sorry, on U and something else, which results in V, then we have this edge from U to V. And also, if you have some sort of nested encryption, encryption involving these E1 and E2, which are arbitrary sequences of, you know, sort of nested encryption operations, and, you know, somewhere in the middle, this encryption under key U, of value v, then you also draw an edge from u to v. And I'll go over an example on the next slide, which hopefully will make this a little bit clear. But maybe what you should realize is that the folklore construction is easily captured, but also much more general solutions, right? Because we allow for these nested encryptions, and also, you know, in the actual paper itself, we also consider these secret shares and PRFs, even dual PRFs. And so, yeah, it really captures a much more general picture than the folklore construction. Okay, so here's an example.
So I have a question, Alex. Like,
Oh, yeah.
So when you were working on this project, and I mean, it seems like that most of the primitives that you use in your grammar are symmetric primitives. Like, you know, this is a common thing between all of them. So for example, like, was there a reason you didn't include any public key primitive into the grammar, or was it, you know, just wanted to see if there was a reason?
Yeah, it's a good question. Yeah, I mean, I guess our view is, you know, again, maybe comparing to black box separations again. With both black box separations and the symbolic lower bounds, it's sort of like you start with certain primitives and you say, with these primitives, you can't get something else, right? And so as you add more and more primitives, things get very, very complex, right? Sort of out of hand almost, right? And so what we wanted to focus on were those primitives that seemed useful for this primitive. And, you know, because it's sort of, you know, one, in some sense, I mean, there's a server and a client, but sort of the functionality is only one party, right? Like, you have a client which can store asymmetric keys. So like, why it doesn't necessarily seem useful to use public key operations, right? And so, yeah, we could have maybe allowed for public key encryption, for example, but, you know, maybe this would have made the proof much more complicated, the model in general much more complicated, and we didn't necessarily see the use for it. So, and then we decided against it. Yeah.
Oh, thank you.
Yeah. Okay, so yeah, here's an example of a key data graph. So let's say this key K1 is stored in the secret cell, and we have a bunch of ciphertexts. And basically these solid lines in the graph here just mean that, you know, for example, K1 encrypts K2, but we also have this nested encryption here and also down here, where basically we have an encryption under key K2 of an encryption under key K3 of element D3. Okay, and yeah, of course we could go all the way and have even S keys in the client storage. Okay. So now let me give you some intuition on maybe a subtle observation that needs to be handled in the proof. So let's say with this structure, the protocol needs to overwrite element D3. Okay, then for forward secrecy, of course, it needs to forget at least K1, right? Because with K1 by correctness, the adversary would be able to get D3. But then also, it needs to forget either K2 or K3, or of course both, but you know, this probably wouldn't be a wise decision. Okay, and so the protocol has the choice in deciding which key to forget. Okay, so yeah, I guess we sort of need to keep this in mind when writing our lower bound proof. But let's say that in addition to K1, the protocol forgets K3. In this case, we say that basically all of the ciphertexts that were created using keys K1 and K3 become useless. Okay, because using this entailment relation, the protocol can sort of no longer glean any information from them. Okay, so yeah, based on this intuition, let's build up to the main theorem. So first, we have lemma 1, which says that each data entry must have a path in our key data graph from a vertex representing an encryption key in a secret cell. Right? This is for two reasons. First, correctness. All data entries need to be somehow derivable according to our entailment relation. And also for privacy, data entries and keys that encrypt them can't just be stored in the clear on the server, right? Because this would trivially violate forward secrecy. Okay, so that's lemma 1. And then our second lemma on the way to the main theorem is just a general graph theoretic lemma. So for any graph that's like of this form, of this form sort of described by lemma 1, if we randomly choose a data entry, then the corresponding path from the secret cell key that must exist by lemma 1 to that data entry has expected out degree log n over s. Okay, I mean, yeah, I guess that probably should sort of be intuitively true to you, and I won't go into the details too much on it, but yeah, that's like a very important general graph theoretic lemma that we provide. And then putting these two together for the theorem, if we choose a data entry randomly to overwrite in each operation, then in expectation, the contents of log n over s server cells become useless for each operation, right? As I said on the last slide, because you need to forget everything on this path from the secret cell to the data element in the graph. And because of that, everything that sort of hangs off of it becomes useless. And yeah, by lemma 2, this is a log n over s in expectation. Okay, and yeah, to deal with this subtlety on the last slide that I was talking about, where in some cases the protocol might have the choice in which path it needs to forget these keys along, right? So like lemma 1 says there must exist at least one path, but there might be many paths, and the adversary just needs to, the protocol just needs to choose one of them to forget. Okay, but by lemma 2, this holds for any graph. So if for each step we just consider the graph with the minimum out degree paths to each data entry, then no matter which path the protocol chooses to forget, its out degree must be at least that of the path with minimum out degree, right? And so then that's how we get around that subtle detail. So yeah, any questions on the lower bound in general?
I have a question.
Sure.
I just wanted to know if there's some kind of uniqueness constraint. Like, is there a constraint that every data entry must have at least one unique key on its path or something like that? The reason I ask this is because I'm imagining something like a star, like you have like one key that works. Why can't you just have like paths out to all the data entries? Does that make sense?
Yeah, I mean, that probably wouldn't be a good protocol, right? Just because,
Right. So
but
I
yeah,
guess
I mean,
I'm
more
asking, are there
generally,
any
like, no, for
constraints?
example, the folklore solution is captured by our solution,
Mm-hmm.
in which, yeah, there, each key that is used for a data element is shared with at least one other data element, right?
Right.
So yeah, there's no restrictions
Mm-hmm.
as long as if you follow this grammar.
I see.
Yeah.
Okay, thank you.
Sorry, I also have a question, clarifying question. Maybe I didn't understand it. Well, can you please go to the last slide, the slide before this?
Sure.
So if my question is that if I'm changing D3, so I'm overwriting D3, I'm not sure I understand why do I need to delete K1 and K2 or K3? Like, why can't I just delete K1? Like, still I am breaking the path to
Sure.
D3, right?
Yeah, so yeah, maybe I should have been more clear, but the model that we consider is sort of the adversary always sees what's stored on the server, and then it can corrupt the client storage at some point too, right? So if this K1 is, so you were saying, sorry, you're saying, why do we need to, so yeah, let's say we only delete K1, but somehow we still remember K2 and K3.
But aren't they encrypted? Like, my question is that K2 and K3 are on the server side, right? And they are encrypted under K1. So if we delete K1, if we forget and K1, then the adversary cannot possibly get K2 and K3.
Yeah. Okay, sorry. Yeah, I see what you mean. By forget, I mean, like, you also, like, you can't use K2 or K3 in the future.
Oh, okay.
Yeah, so like you need to lose all information on K2 and K3 in the future. So like, yeah, as you said, if you delete K1 and sort of, don't do anything with the ciphertext of K2 and K3 before deleting K1, then this is what I mean by forgetting K2 and K3 or K3. Yeah.
Okay.
Yeah.
Thank you.
Mm-hmm.
So I have a question related to what Marilyn was saying earlier.
Yeah.
So I think that maybe, so the way how I understood Marilyn's question was that that's true that in your grammar, you don't have any rules on how you specify the key, right, Alex? Like, you don't have any rule on how you sample the keys or sample the randomness. So I think that one question she had is that, like, since there is no rule, then everything should be implicitly captured. Like, if I decide to instantiate the way how to sample my keys, not just arbitrarily, not uniformly at random, that some of the primitives, for example, require. Like, just I will pick, for example, in a counter-based fashion, like I will pick key 1, like to be string 0, I will add just 1 in a binary fashion to the key 2, and maybe this will create issues. Or, for example, I will reuse keys. I know that this is a crappy construction in some sense, but still, like, from a grammar perspective, the way how you set out the rules, like, there is, I mean, maybe I'm wrong because I don't remember the paper, but it seems like there is a need to specify how the randomness, or there is an assumption maybe implicit there that the keys should be uniform or whatever, like, distribution for the primitive to work correctly.
Yeah, so you're certainly right. I guess there's sort of an implicit assumption. So maybe let me go back to where I put the grammar. Okay, yeah. So there's sort of like an implicit assumption that random strings are sampled uniformly at random by the way that the symbolic model is structured itself. Because basically, how it works is, like, if the protocol wants to use a random string, then basically it just gets the symbol R, which can't be sampled by anyone else. Like, that's the way you should think of it. so like this is certainly a limitation of the symbolic model, where like if you had a protocol that maybe like played with bits, or if you're using like group elements or something, somehow played with the algebraic structure of the primitives that you're using, this is not captured by the symbolic model.
Okay, so basically, like the way how we should read this grammar is that like whenever we talk about random string is uniformly sampled.
Essentially, yes.
Okay.
Yeah, and this is like, so yeah, if you go back to the like original Michiancio Panjwani paper of 2004 that used this lower bound for multicast encryption, actually, which I'll talk about later, they sort of sweep a lot of this under the rug. And yeah, I think like in the paper, we tried to clear up a lot of it, but it is sort of a, it's a bit of a confusing model in a sense, because it is a little bit skewed from reality, but it does seem to capture reality pretty well in some sense too. And I think there are actually like a number of papers that sort of look at cryptography in general in a sort of like abstract symbolic way like this. So I mean, like if you think about like, I mean, I'm not an expert on this stuff either, but if you think about like how things are formally verified, like how cryptographic protocols are formally verified, it's using a very similar framework as this, right? I mean, it all goes back to like, programming languages literature as well, right? Where you have some sort of grammar. And yeah, there's some papers that like prove at least some equivalence between proving security in this symbolic model and proving security in an actual computational model. But yeah, it's certainly like a sort of a confusing model, definitely.
Okay.
Okay, yeah, any other questions? Okay, then yeah, I guess that's it for the lower bound intuition. So now I'll talk about some of the applications of this primitive. And so yeah, at the beginning I said somehow we are circumventing the lower bound. And so how we do this circumvention is we focus on primitives that are already tree-based constructions. And if you wanted to naively compose these constructions with the folklore FS-ERAM construction, then you would get log squared complexity. But yeah, the main intuition is we will overlay this folklore FS-ERAM tree with the tree of this whatever construction that we're considering to get log n complexity in total, right? So like if we have this red FS-ERAM tree, for example, and combine it with the blue tree of some other primitive, then we get this sort of purple tree, right? So yeah, in more detail, let's talk about our first application, which is called FS memory checkers. So yeah, for FS-ERAM, we sort of critically require or assume that the server returns the correct cells that were stored on the server, right? But this might not be the case. The server could potentially adversarially tamper with them if it wanted to, and so this requirement is something that memory checkers provide, which is like if you outsource some data array, then even if the adversary is allowed to tamper with what you outsource in some way, you're still guaranteed integrity of the data somehow. And so yeah, FS memory checkers just somehow combines both of these concepts. So you still get forward secrecy of the data, but also if the adversary somehow tampers with what you outsource, then the protocol should notice and, you know, output error or something. Okay, and this should hold even if the client state can be corrupted. Okay, and so the high-level intuition for this is you overlay, you know, the classical Merkle tree construction for memory checkers and this FSERM folklore construction. And with this, you get our log n overhead, which we want, which is optimal with respect to both our FSERM lower bound and then also the most optimal memory checker construction. And yeah, I say this, there's a small caveat where the best lower bound is actually slightly sub-logarithmic for memory checkers. But yeah, the best actual known construction is still logarithmic. Okay, so yeah, maybe a quick review of Merkle trees. Basically, each node is just the hash of its two children. And on the client side for this memory checker, you just store the root hash. Okay, I think probably everybody's pretty familiar with that. So now the construction of our FS memory checker, again, overlays these two concepts. So looking at maybe the left two children, left two leaves, we have in these leaves the encryptions of the two data elements under the key that's at the parent. And then we also, at this parent, store the hash of these two ciphertexts. Okay, and we do the same for D3 and D4. And then if we look a level up, we have, as in the FSERM, we have the encryption of K00 and K01 under the parent. And then also at the parent, we have the hash of both, the hashes at 00 and 01, along with the corresponding ciphertexts. Okay, and then we build the rest of the tree like this. Okay, and so yeah, for this hash function, you can either consider collision resistant hash functions, or if you want something in the standard model, then you can just use Wolf's universal one-way hash functions. But then you also need to provide the description of the hash function itself at every node, which sort of requires more space. And yeah, another option could be, instead of doing this, encrypt and hash, you could just use sort of like forward secret authenticated encryption, but then you get slightly less security, right? Because if the client storage is leaked, then the adversary gets the AEAD key stored at the root, with which it can sort of forge invalid ciphertext, right? So you get slightly less security, but I guess yeah, it's not super important. So yeah, let's talk about the operations briefly. The read operation is just the same as the folklore FSERM construction, but you also check that the hashes are correct along this path, the direct path, as you would for the memory checker construction. And if there's a mismatch in one of the hashes, then you output error. And it's the same thing for the write operation, where you also need to regenerate the hashes. Okay, and for efficiency, it's asymptotically the same as before. And the security intuition is, the root key and the hash, which is stored locally and only seen by the client, before corruptions at least, ensure that ciphertext at the children decrypt correctly, while also ensuring privacy. And then you can sort of inductively follow this argument all the way down the tree, right? So doing this at level I ensures these same guarantees at level I plus 1. Okay, so yeah, any questions on this construction? Okay, yeah. So let's move on to oblivious FSERAM then. So yeah, as you can probably tell, it's sort of a combination of FSERAM and ORAM. And so for FSERAM, we don't require the pattern of reads and writes to be hidden. But of course, this is the main point of ORAM itself. But ORAM doesn't allow for the leakage of client state. And the question that we pose is, can we combine these notions? And so unfortunately, for the strongest way that you could combine these two notions, meaning that after a corruption, you not only get forward secrecy of the stored data, that has since been overwritten or deleted, but also the access pattern of the previous operations must be oblivious as well. And we actually show a lower bound in the unconditional cell probe model that's big omega of n, meaning that the trivial solution of just downloading everything and re-encrypting it would be the optimal solution. And I can, if people want later, I mean, the intuition is pretty brief on this. But yeah, we're running low on time, so maybe I'll skip it for now. But yeah, what we can achieve is both modulo client leakage. So what I mean by this is, if there is a leakage, then we can get forward secrecy, but the access pattern won't be hidden. And similarly, if there is no leakage, then the access pattern can be hidden, and we sort of get vacuous forward secrecy. Okay, and our construction will have big O of log n times f of n overhead, where f of n is any function that's little omega of 1. And yeah, those of you familiar with path ORAM, this is a result of us using path ORAM, which is, I'll talk about it on the next slide. Yeah, and so this is, beside this little omega of 1 factor, this is almost optimal with respect to both the FSERAM lower bound of our paper and the ORAM lower bounds that have been constructed in the past. So yeah, what's the intuition? Basically, if we use tree-based ORAMs, path ORAM being one of them, then we can overlay the FSERAM construction onto this tree. And so there's actually a subtle problem. Tree-based ORAMs actually require log squared overhead. But in the past few years, we've had a lot of progress in ORAM. We actually have optimal log n overhead hierarchical ORAMs. But with these, we can't overlay the FSERAM construction. It's a very, very different structure. And so what we do is we take parts. I mean, I guess we use the general tree-based ORAM constructions, but for parts of them, we actually use the hierarchical ORAMs. And what I mean more specifically is we replace the position map that is used in tree-based ORAMs with a hierarchical ORAM. And I'll talk about it a little bit more now. So yeah, in tree-based ORAMs, you have what's called you have what's called a position map, which basically maps virtual cells to the leaf to a leaf in the tree that is used in the tree-based ORAM, which this data is associated with. Okay, and usually this is like a part yeah, I mean, this is a part of the path ORAM construction, and they like use this clever trick to deal with it. But what we do is we just store it in a hierarchical ORAM. Okay, and then you have the rest of the construction itself, which is just a tree. And in the root, we have sort of the FSERAM root key K epsilon. And then at every node, you have a constant number of encryptions of the data items itself that are in this subtree. So they aren't themselves in the subtree, of course, but their corresponding leaf in this position map is in the subtree, right? So like 5 is here and 8 is here, let's say. That means that they can be stored in this tree, sorry, in this node, but like the data element here would not be able to. Okay, and then you also need some dummy encryptions as well, just so that everything looks the same. And yeah, all of these items are encrypted under this K epsilon. And then you additionally, as in our FSERAM construction, have an encryption of this K1. Okay, and then you additionally have this sort of stash of extra items that aren't in the tree right now that are encrypted also under this K epsilon. Okay, and so yeah, just quickly, and then we'll probably have to stop. For reads and writes of virtual cell I, first you look up I in the position map, which is log n, by the construction of the hierarchical ORAM. Then you retrieve the direct path and copath of I's leaf and decrypt it as an FSERAM, which is of course log n overhead. You retrieve and decrypt the stash, which is of size, little omega log n, so it's that much overhead. Then if it's a read op, you just return this data element eventually, but also continue here. And if it's a write operation, then you actually, update the data at I to di prime. And then you choose a new leaf for I uniformly and store it in the position map, which again is log n overhead. Put it back in the stash with its corresponding leaf as a label, encrypted, of course. Then, as in path ORAM, you greedily evict items from the stash to direct path nodes of I's old leaf. And again, you only put an item in the node if its leaf is in the subtree of the node. And so this is, of course, log n overhead again. And then finally, you regenerate the keys for the FSERAM and do the re-encryption and also re-encrypt the stash, which is, this should actually be little omega log n overhead. Okay, and so obliviousness follows from 1, the obliviousness of the position map from hierarchical ORAM, and then also, just standard, the usual security of path ORAM, where basically all that the adversary sees is just a download and re-encryption of some random path. Okay, so yeah, any questions there? And I guess maybe I should probably stop there as well. I have some more slides, but we're at an hour now.
No, I think that this is great. Maybe like we will stop here because we are five minutes past the time. So
Sure.
It's lunchtime. So no, this is great. So I was thinking about the stash, like for the ORAM construction, and I convinced. So when you were talking about it, like I convinced myself that there is no issue, because like I was thinking that when the adversary corrupts the client state, it gets to see the stash, and I was thinking maybe there is some old data there that remains in the stash, but in path ORAM everything is refreshed right away. So I was thinking maybe in the setting where, let's say that you do a write in the ORAM, like in path ORAM, you fetch the data item, and maybe you didn't finish the write process yet, and you got corrupted. I think maybe at that point in time, maybe there is loss of, it might be that there is a loss of forward secrecy in the sense that it can get to see the data item before being overwritten. But then, like, it's kind of like a very special case. So
yeah, and I mean, in fact, you would maybe even have problems with obliviousness there as well. I mean, I'm not really sure, but yeah.
Yeah, I think that we have, we had already so many questions, and yeah, thank you so much, Alex. And I mean, I don't know if somebody has any question. Yeah, if not, yeah, thank you, Alex. I just noticed we didn't thank you for the talk. Thank you for the talk. It was great.
Oh yeah, of course.
Yeah.
Thank you. Yeah, thanks for inviting me again.